In the previous section, we scaffolded the basic components of our UTXO project. In this section, we'll get into the cryptographic security of our chain. In fact, there are many vulnerabilities that Bitcoin defends against, which we'll need to implement here in our spend function. Namely, we need to ensure that each output that the user wants to create from his transaction is defined exactly once and has a non-zero value. We also want to make sure that the total output value must not exceed the total input value. Hence, we're not creating value from thin air. We want to check that the new outputs do not collide with existing ones, which we've actually already implemented through our UTXO storage hash implementation. And specifically, we want to ensure that replay attacks are not possible, and that the provided transaction input signatures as a part of every input UTXO are actually valid, and that those signatures do indeed sign over a spendable UTXO, and that the signatures also sign over the entire transaction, ensuring that the transactions are tamper-proof. Let's come back to this to-do that we previously left alone, and think a little bit about what we want to do here. We know we want to validate our transaction here using a function that takes in this transaction variable and returns a result of OK or error, like the other functions here. Now, it would be quite elegant here for this validate transaction function to return a result containing the value reward. Since we're very likely iterating through the transaction inputs and outputs vectors in this function, let's calculate the reward in here in one fell swoop. So let's let the reward equal the result of validate transaction instead of this empty value. And of course, we're missing this self syntax here. So next, let's go ahead and create a helper function called validate transaction. Inside your module trait implementation, let's go ahead and declare a public function called validate transaction, which takes in a transaction reference to a transaction type object and returns a result containing the value, i.e. the reward value, or a static error string. Let's go ahead and copy over our list of security checks that we actually need to implement here. We'll start off by validating the initial basic requirements in this transaction. And the function that will help you do this is called ensure, which we've imported from frame support up here. First, we want to ensure that the transaction has valid input UTXOs and valid output designations. So let's go ahead and ensure that transaction.inputs, the inputs array, is not empty. And if it is, this ensure macro allows you to designate the error message that will be returned in the form of a static string. So in this case, we might want the error message to just say no inputs. Similarly, we'll want to perform the same check for the outputs array that we're expecting in transactions. Next, we'll want to check that each input is used exactly once and that each output is defined exactly once to avoid cases like double spending. We're going to use a special substrate data type called the B-tree map, which essentially just lets us do additional things to our data set, like the ability to sort it efficiently or the ability to get the unique set of a particular collection of data. So to do that, we're going to want to go ahead and create something called an input set and an output set that are both B-tree maps. Now, we're most likely not going to be using these B-tree maps throughout the rest of this function, so it would be good practice to declare these one-time use variables that are stored on the heap within a Rust function scope. Now, if you're new to Rust, this just means that any new variables declared here on the heap will simply be discarded at the end of this specific scope. So let's go ahead and create our input set, which, as we mentioned, is going to be a type B-tree map. And this B-tree map will have a key of underscore, so whatever key is being returned here will be the type of the key going into the B-tree map. And it'll have a value of something like a nil field. And we want to set that equal to transaction inputs vector turned into an iterable. And then we want to go ahead and map it into a B-tree map where the key is the input itself and the value is just any object. We don't really care. And then we want to go ahead and collect that into this type B-tree map. So within the execution of this closure, what's actually happening is that we're deduping any potential duplicate inputs. So at this point, we can go ahead and do another ensure check and ensure that the length of the input set that we've just created is equals, in the ideal situation, to the original inputs vector that the user inputted. And if this isn't the case, well, we know that the issue is that each input must only be used once. In the same exact way, we can do this deduping and check for our outputs array. So let's just copy over this implementation. And this will be our output set, and we'll be iterating and deduping over our transaction.outputs and verifying that the output length should be equals to the transactions.outputs length. And if that's not the case, then each output must only be defined once. And if that's not the case, then we want to make sure that the error message is in fact each output must be defined only once. Okay, so with these basic checks in place, we're now able to finally iterate over our input UTXOs as well as our output UTXOs to do all of our checks and ensure that the signatures are valid. So first, let's go ahead and iterate over our transactions input vector. So for input in transaction.inputs, turning this into an iterable so that we can actually do the for loop. And the first thing we want to do here is retrieve the input UTXO from our UTXO store that the user is trying to reference. So if let sum input UTXO, and I'll explain what this means shortly, reaching into our UTXO store variable and getting the out point for what the user is trying to spend in his or her transaction. Now, if you're new to Rust, what this line is essentially saying is attempt to get this particular hash from this hash map. And if that hash exists, I want to name the return value. And recall this get function will return an option which contains the actual UTXO. Then I want to name this UTXO that I'm successfully getting back input UTXO. Now, if this statement fails, it actually means that this UTXO doesn't exist. So we'll want to handle that condition later on. Now, if we are able to successfully retrieve the UTXO, this is the point where we want to check the signatures. So the way to do that is with another ensure. Now, in our implementation and in most Substrate implementations, the particular signature scheme that we're using whenever we sign something or we verify the signature of something is called SR25519. Let's look at the reference documentation to just check what this function does. So we can see that SR25519 verifies whether or not a particular signature indeed signs over a message and indeed uses the private key that needs to correspond to this public key. And those are the three input parameters in here. Let's actually step into this function within Substrate documentation to see what it does. So SR25519 returns a Boolean, and it returns true when it is able to successfully verify that a particular message, this particular raw encoding of a message, was in fact signed by the private pair of this corresponding public key. And that's what's reflected in the signature here. So coming back to our implementation, recall that this SIG script value here needs to be signed for this particular input by Alice's key over all of the transaction variables. So that's the check that we want to do within this line here. And the way to do that is to pass in first the signature, converting it into the right format. From the user input, and we want to pass it in as fixed bytes. And for the message, what we need to do is take this input transaction and actually go ahead and extract out, so delete all of these SIG scripts here, and then check that Alice has signed over something called a simple transaction. For the second field, what do we expect Alice, for example, to have signed over? Well, recall the original explanation. We expect her to have signed over the entire transaction with the signature field extracted. Now in Bitcoin, this entire transaction without the signature fields is called a simple transaction. So we'll be implementing something similar. To do, we'll need to somehow calculate a simple transaction as well to be used in this signature verification function. And then lastly here, we'll be expecting the public key for whoever owns this particular input that we're iterating through, in that the user is trying to spend in this transaction. So to retrieve that, we'll do public, which designates a public key type. And since the way that we're storing public keys in our implementation is as a H256, we'll just need to do a simple conversion back into the public type that this particular function is expecting. And then doing input utxo.pubkey helps us retrieve the public key that this entire signature should verify against. Now at this point, if this signature verification step fails, then we know that this entire signature was not valid, and we'll want to emit the error message, signature must be valid. Let's delete the extra parentheses here. Okay, so now we need to follow up and actually implement this simple transaction, namely taking in a transaction and stripping out all of the SIG script fields in its inputs. Why don't we create a helper function to help us do that? So very simply, I want to call this helper function getSimpleTransaction. And it'll take in a normal transaction, or a reference to a normal transaction type. And I want it to output for me a vector of unsigned 8-bit integers. So this is the same format that Substrate expects whenever you encode something into its serialized format. And it's the final format that this SR25519 verify function will be checking for. So within this function, let's create a new simple transaction type that's mutable called transaction, or TRX for short. And let's initialize that by cloning the original transaction. Next, we want to iterate over the transaction inputs, and to make whatever we're iterating actually mutable, we want to do .itermute. And stepping into each SIG script, we actually want to go ahead and remove whatever signature is being passed in, replacing it with a H512 type that's essentially a hash of all zeros. So it looks like this. And finally, with the SIG script fields removed, we want to return a encoded version of this transaction. Coming back to our validate transaction function, we want to go ahead and use our new helper function to get the simple transaction. So let's do let simple transaction, be equal to invoking our internal helper function, get simple transaction, making sure to pass in the transaction. At this point, we know that whatever input UTXO that this user is trying to spend in this transaction is valid. So a good thing to do here is to start tallying the total value of all of the inputs so that we can later do a sort of checksum check. So up here, to clump all of our variable declarations together, let's instantiate a couple more mutable variables, namely a counter of the total input, which will be of type value that starts off as 0, as well as a mutable total output, which also starts at value 0. And then coming back to here, after we've verified the signatures, let's go ahead and tally up the inputs by doing total input should be equal to the former total input, a type safe checked add to this current input UTXO's value in this for loop here. And if anything goes wrong, we'll signal that the input value has overflowed, unwrapping this added value to the total input tally. Okay, so now let's consider the scenario for what happens if we weren't able to get the designated UTXOs in our UTXO store. If the UTXO doesn't yet exist, what's actually happening? It could be one of two things. The user could either be just referring to a fake UTXO and trying to spend something that doesn't exist, or in the other valid scenario, we could be coming across a race condition. In a blockchain network, whenever you make a transaction, you submit it to your nearest node. Now, depending on your network latency and other variables, it's very possible that very valid transactions are not sent to many nodes in order. This means that you could be spending a valid UTXO that you got from, say, Alice, and you're trying to spend it on Bob, but the particular node that's verifying your transaction hasn't received Alice's transaction yet. This is a very valid race condition that we'll be taking care of later in this workshop. For now, let's just put in a to-do reminder to remind us to come back to this. Next, we're going to want to iterate over our outputs and ensure that all of our outputs are valid. Similar to what we did above, let's go ahead and for each output in the outputs that are being passed in via this user's transaction, let's iterate over the outputs vector. And let's first ensure that the output value is bigger than 0, that the user isn't trying to create empty UTXOs that are essentially useless. And if not, let's go ahead and return the error message, output value must be non-zero. Okay, next, and this really shouldn't happen because we implemented it to be quite safe, but we still want to go ahead and check whether or not if we tried to hash and store this particular output in our UTXO store, there would be a collision. So let's go ahead and calculate hash, taking the hash of a pointer to a tuple of the transaction encoding, as well as the output index. Now, this is something that we're going to need to track as we iterate through the outputs. So let's go ahead and declare an index variable that we need to be tracking. So let mute output index of type U64 that also initializes at 0. And let's not forget to increment this output index every time we go through this loop. So output index is equal to the previous output index plus 1. And if something goes wrong, we know that the output index has overflowed, unwrapping its value to be returned. And next we actually want to perform the check and ensure that our UTXO store, as it stands now, doesn't yet contain this particular hash that we just calculated. And if so, we'll want to return an error message along the lines of output already exists. And similar to how we were keeping a tally of the total inputs, we'll want to do the same thing here. Let's tally up our total outputs at this stage. So let's do total output should be equal to the current total output plus the value of the current output in our iterable. And if something goes wrong here, we'll know that the output value has overflowed. And last but not least, after all of these checks, we can change the state. Great. And that is the last check that we need to do here. At this point, we conveniently have the sum of the total input value and the total output value, which gives us enough information to calculate the particular reward from this transaction. But first, let us ensure that we are not overspending by checking ensure that the total input is still greater than or equals to the total output, that the users aren't creating value from thin air. And if something goes wrong here, we'll know that the output value must not exceed the input value. And after that check, let's designate that the reward should be equal to the total input subtracted by total output. And again, doing a OK or check to make sure that the reward has not underflowed. And finally, rather than returning a result of OK with an empty tuple inside, we can now return the reward value. And coming back to how we're originally intending to use validate transaction function, that's exactly what's expected. Let's go ahead and do a compiler check to make sure that everything compiles. There's an error here where the variable reward is not found in the scope. That is because we never declared it. Let's go back and easily fix this by declaring this variable. And let's check with our compiler again.